So now that we've learned a little bit about parametric equations and parametric curves, it's time to jump back into calculus. So 7.2 is all about finding derivatives and integrating parametric equations. In this video, we're going to concentrate on the derivatives of parametric equations. So in the box here, you will see that finding the derivative of a parametric equation is really a simple process. We have our two parametric equations. We have x as a function of t and y as a function of t. So if we take the derivative of x as a function of t, in other words, x prime of t, and we take the derivative of y as a function of t, that would be y prime of t, and we divide y prime of t by x prime of t, we have the derivative of dy dx. Now be careful with the terminology. What we are looking for is the derivative of y with respect to x, not with respect to t, the parameter. We want to find the derivative of our two variables x and y. So to do that, we need to use the parametric equations. We find dy dt, we find dx dt, and we divide them. So let's just jump right in and look at the first example. So in this example, we have x is a function of t, t squared minus 3, and y is a function of t, 2t minus 1, and we're looking at the interval from -3 to 4. So the way that I usually like to do it is let's just start off finding my derivatives. So x prime of t, in other words, the derivative of x with respect to t is 2t. The derivative of y with respect to t, or y prime of t, is equal to 2. So pretty simple derivatives. Well, then using the formula from up above, dy dx is simply dy dt divided by dx dt, I'm sorry, dy dt divided by dx dt, but I usually like to skip that part and go right to multiplying the numerator by the reciprocal of the denominator. Okay, it just saves a step. Okay, so that's what I've written here. But that's the same thing, I think we can all agree as that. So then we end up with 2 divided by 2t, which is 1 over t. So the derivative of y with respect to x is actually in terms of our parameter t, and that's the way it is going to work. Now, in this particular example, they also said to locate any critical points. We're not doing anything with those critical points, but this is just a good way to start thinking about critical points again. Remember, by definition, a critical point is where the first derivative is equal to 0 or is undefined. In this particular case, the first derivative is undefined at t equals 0, because we can see that if we let t be equal to 0, we end up with division by 0, and that would make it undefined. If we were to set 1 over t equal to 0, then we would end up with 0 equals 1, which is a contradiction. There is no such thing. And so therefore, there are no values of t where the first derivative is equal to 0. And therefore, the only critical point is where the first derivative is undefined. Second example. We have x as a function of t is 2t plus 1. And so the derivative of that, I forgot my x, or I wrote it as dx dt. Derivative of x with respect to t is 2. And y as a function of t is a cubic polynomial. And so the derivative of that with respect to t is 3t squared minus 3. And so we have dy dt times dt dx, which is the same thing as dividing by. So we're basically dividing them. And we end up with this. And then I like to write that in this form, but either form would be acceptable. I just find this form a little bit easier to work with. And now to find the critical points, as I mentioned in the previous problem, the critical points are either where the function is equal to 0 or where the function is, the derivative is undefined. So we can set the derivative equal to 0. Solving it for t, we end up with t is plus or minus 1. So that's just some basic algebra. And then where is the first derivative undefined? Well, there are no values of t that will give us division by 0 because it's a quadratic polynomial. And so it is defined over its entire domain. It is not undefined at any point in its domain, particularly in this range from -2 to 5. Okay. Now, here's a good old tangent line problem from Calc 1. So find the equation of the tangent line to the curve defined by the equations. And so if this looks like I wrote something in here, it's because I did. I kind of made a mess of it, but I think that's the correct problem. So once again, in order to find the equation of a tangent line, we need to find the derivative. And so let's find the derivative of x with respect to t. And so that would be 2t. The derivative of y with respect to t is 2. And once again, we've already done this problem. So dy dx is equal to 1 over t. All right, so that's the derivative of y with respect to x. And we want to find, in order to find the equation of the tangent line, we need the slope of that tangent line. And so the first derivative is the slope, but we need the slope to be in terms of y's and x's. We need our equation to be in terms of y's and x's, not in terms of the parameter. So what we're going to do is we're going to let, when t is equal to 2, we substitute that into our derivative. And so at t equals 2, we end up with dy dx is equal to 1/2. And dy dx is the slope of our tangent line. So it's just a matter of finding our derivative, dy dx, and then evaluating that derivative at the value of the parameter that we're interested in, and that will give us our slope. All right, now, another thing that we need, and I'm coming down, I'm just going to jump ahead here. I'm going to be using this formula, the point-slope equation. And to use the point-slope equation of a line, we need the slope, and we need a point on the line. And so the slope we know is m, that is the slope. And so we need a point x1, y1, which is a point on the line. Point on the line. So how do I get that point on the line? Well, once again, I go back to my parameter, which is t equals 2, and I'm going to substitute that in to both of my parametric equations. So in other words, when t is equal to 2, we're going to find out what x is equal to. Well, x is simply going to be t squared, or 2 squared, minus 3, which is 1. And then we substitute the parameter into y. So y of 2 is 2 times 2 minus 1, which is 3. So this gives me when t is equal to 2, x is equal to 1, and y is equal to 3. I'm going to write that as an ordered pair. Okay, that ordered pair then becomes my x1, y1. So now I have everything that I need. I have the slope of the line right here, and I have a point on the line. From here, it's just a little bit of algebra. We substitute all those values into the point-slope form of the equation, and I like to write my final equation. There's lots of ways you can write an equation. I always like to write my equation in the form y equals mx plus b, which is the slope-intercept form of the equation, and that's the form that this is in right here. Let's do another one of those. So in this case, so again, we start with our basic point slope form. What do we need? We need the slope and we need a point. So the first thing I'm going to do is find the slope. The slope is the derivative of my equation. So starting with parametric equations, we find x prime of t and we find y prime of t, both fairly straightforward derivatives. Then I can find dy dx by simply dividing dy dt by dx dt. And then at t equals 5, we substitute in 5 for t in the numerator and in the denominator, and we end up with 24. That then becomes my slope. So the slope is 24. So when t is equal to 5, the slope of the tangent line to the curve at that point will be 24. Now I need to find my x1, I1. And so we go back to the parameter, t equals 5, and we substitute that in for t in the equation x, t squared minus 4t. So we have 5 squared. I did a little bit of erasing here, so that's an equal sign. 5 squared minus 4 times 5, which ends up being 5. And then we substitute it into the y equation, and we end up with 220. That gives me an ordered pair, which is the x value is 5, the y value is 220. So I now have everything that I need to write my equation in point slope form and then rewrite that in slope intercept form. So we substitute in 220 for y1, 24 in for the slope, and 5 in for x sub 1. Do a little bit of algebra on it, and we end up with 24x plus 100. So that is the equation of the tangent line to the parametric curve at the point where t is equal to 5. Next up, second order derivatives. These are fun. So we know that in normal functions where y is defined as x, we find dy dx, and then we take the derivative of dy dx, and we find d squared y dx squared, or the second derivative. Same idea, but slightly different here. The second derivative of y with respect to x, and this is just the same, saying the same thing. What this is saying is we are taking the derivative of dy dx with respect to x. Let me say that again, because it's going to be important understanding what we're doing here. This tells me I'm take the derivative of dy dx with respect to x. Okay? To do that, we use this formula. Okay? It's not just a matter of taking the straightforward derivative of the derivative. And the way the numerator is written is a little confusing. So I'm going to rewrite that down below here. Okay, I'm going to rewrite that where I have a little bit more space here. What this is saying is take the derivative of, and I'm going to write this the same way I wrote that this is written, take the derivative of dy dx with respect to t. That's the numerator. Okay, that is the numerator. So we're taking the derivative of dy dx. So we found dy dx. That's our first derivative. And now we're taking the derivative of dy dx with respect to the parameter t. It makes a little more sense when you write it this way. And then we are dividing that by dx dt, which we've already found. All right, so let's see how that looks when we actually do it. So here is my dx dt, 2t, and here is dy dt, or y prime of t, from my function of y. Then, finding dy dx, is simply dy dt over dx dt. And so we've done this a couple of times now. We end up with 1 over t. And now here comes the new part. This is finding the second derivative of dy dx. We want to find the derivative of dy dx. We're taking the derivative of dy dx with respect to t. All right. And so we're taking the derivative of 1 over t with respect to t. We end up with negative t to the negative 2. And of course, you guys can handle that because 1 over t can be rewritten as t to the negative 1 power. And then taking the derivative of that, you have negative 1 t to the negative 2, which then is better written as negative 1 over t squared. Then, to find the second derivative, I'm going to use a different color now. To find the second derivative, we take the derivative of dy dx with respect to t and then divide that by dx dt. And so we take this, that becomes our numerator, and then we go back over here to dx dt, and that becomes our denominator. And then that's it. That is our derivative. And we just have to simplify it. And so when we simplify it, we end up with negative 1 over 2t cubed. That is the second derivative of y with respect to x. In this next example, now in my notes, I've changed that, but there's a little kind of an omission in here, which I will point out as I'm doing this. So we want to find the values of the curve where the parametric equation is concave up. So remember concavity. Real quick review of concavity. We've got a curve that looks like this. That would be some type of a third-degree polynomial curve, actually, but it drives home the point that the part of the curve where it's like a bucket upside down, right in through here, that is concave down. And what you learned in Calculus 1 is that a curve is concave down wherever the second derivative is negative, where f, double prime of x is negative. And then our curve is concave up here, and that's going to occur where the second derivative, f prime double prime of x, is positive. So the moral of the story here is we need to find a second derivative in order to determine where the curve is concave up or concave down. So let's start in on that process. Now this one is going to be a little bit more involved. We actually have to use the product rule and the quotient rule for derivatives. So let's start. Here's x prime of t is e to the t. And we know that's an easy derivative because it is the derivative of itself. Y prime is a product, t times e to the negative t. So we have to use the product rule for derivatives. So I think of it as the first function and the second function in this particular case. I think that'll be a little less confusing than saying f of x and g of x. Let's say the first function and the second function. So t is the first function, e to the negative t is the second. So this is the derivative of the first function times the second plus the first times the derivative of the second function, which is negative e to the negative t. And then simplifying that, factoring out the e to the negative t, we end up with this. All right, so our derivative, dy dx, is going to be dy dt over dx dt. And so we end up with this, but we can simplify that a little bit because we have e to the some power of t in the numerator and denominator. And so that simplifies to this. All we're doing is bringing e to the negative t down to the denominator, making it e to the positive t, and then e to the t times e to the t is e to the 2t. All right, so this is dy dx. Now we need to find the second derivative. So let me get rid of some of this. The second derivative, And so what I should have written in here is this right now is the derivative of dy dx with respect to t. Okay, it should be reflected in my actual notes that I have, the solutions to the notes, but I haven't changed it in the video. All right, so we're taking the derivative of this with respect to t, and then we are dividing it by x prime of t. So first of all, the derivative, we have to use the quotient rule. Okay? So the quotient rule, I have the numerator and the denominator. Here's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. All right. And then cleaning that up, we can factor out an e to the 2t from the numerator, and we have an e to the 4t in the denominator, so that can be simplified. E to the 4t can be thought of as e to the 2t times e to the 2t. When you multiply bases, you add the exponent, so that becomes e to the 4t. And so e to the 2t cancels with one of those e to the t's. And so we end up with this, right? So this right here is the derivative of a second derivative of y with respect to x. No, that is the derivative of dy dx with respect to t. And now the second derivative is we take this and divide it by x prime of t. Okay, I don't have room to write the actual formula in here, but we're using that the formula that we looked at up above. All right, and so we take the derivative here. This then becomes the second derivative of y with respect to x. That's what we're looking for. So again, just to make sure we're all on the same page here, get rid of some of this. This right here is actually the derivative of dy dx with respect to t. So I want to clarify that again. Okay, that is the derivative. I forgot to write all of the notation when I wrote this. That's what we have here. Then the second derivative, go back to our formula, second derivative. So what we did was we just found this, the numerator. Now we're dividing that by dx dt. And so that's what we are doing when we get to this point. All right, once we have all that, what do we need to do to determine concavity? Well, the point of inflection is this point on the graph where the concavity changes. So when we set the second derivative equal to 0, we find the point of inflection. So the point where the second derivative, which is this, is equal to 0, that is our point of inflection. And that divides the interval where we're concave up from where we are concave down. So let's take the second derivative, set it equal to 0. We then end up with 2t minus 3 equals 0, or t equals 3/2. In Calc 1, you learned that a really good way of determining concavity then is to make just make a number line and put 3/2 on the number line. Take a point to the left of it, take a point to the right of it, and plug it into your second derivative. So remember what I wrote up here, where the second derivative is positive, it's concave up. Where the second derivative is negative, it's concave down. So I take the point 1, plug it into my second derivative, and I don't care about the number, I just care is the number positive or negative. And so when I plug 1 into the second derivative, I end up with a negative number, which means we are concave down. And when I plug 2 into my second derivative, I end up with a positive number, which means we are concave up. And so we want to know where it's concave up, I believe, where it's concave up, yes. That means from the point of inflection, 3/2, and to the right of that, which would be towards positive infinity. So from 3/2 to infinity, the graph is concave up. So this is a lot of review of concavity, points of inflection, and I realize I'm going over a lot of this very quickly. Again, you can find some videos on YouTube. The Organic Chemistry Tutor has some videos, and so do a lot of other people, to refresh your memory a little bit on concavity and second derivatives. But that should be enough to get you through this as a refresher. All right, that is it for this video.